Hi guys, Justin again from chemistrynotes.com, and this is video number 3 of section 14, acids and bases. So we've introduced acids and bases, and we were talking about Bronsted-Lowry acids and bases in particular, conjugate acid-base pairs, acid strength at the end of the last video. And then I introduced the fact that water is an amphoteric substance, and then so is NH3. I want to specifically focus on water as an amphoteric substance. Amphoteric, by the way, is just a fancy word that means it can act as either an acid or a base. So why don't we just do an example where water is reacting with water, and in one situation water is a base, and in the second situation water is an acid. So I've just written the Lewis structure for water twice. I'm showing that in the first one water is acting as a base. See how it actively goes out and accepts that H plus from the H2O that's acting as an acid, thereby making the acid the H plus donor, right? And we've learned in previous videos that bases are H plus acceptors, proton acceptors. Acids are H plus donors, or proton donors. And what's the result of my H2O acting as a base grabbing another H plus? Well, H3O plus. And that's the conjugate acid of the first water molecule. Now, what happens to H2O acting as an acid once he's given up H plus? Well, now he's down to only one H, making him OH minus. So the hydroxide ion, OH minus, is the conjugate base of the second water molecule that's a reactant. So from the above, we got 2H2O liquid. Liquid won't show up in my equilibrium expression. Yields H3O plus OH minus in the box. So Kw, the dissociation constant for water, is equal to just the concentration of H3O plus times the concentration of OH minus. There is no denominator because H2O on the left, the reactant, is a liquid. In other words, Kw is equal to concentration of H plus times the concentration of OH minus, and that's always equal to 1.0 times 10 to the minus 14th, assuming we're at 25 Celsius, room temperature, okay? So the next page of notes, it says in pure water or in any neutral solution, the concentration of H plus is equal to the concentration of OH minus, okay? Quote, H plus is kind of like your emblem for, oh, that's acid. And OH minus kind of always represents base. So if acid equals base, H plus equals OH minus concentrations, well, then each one of them must be 1.0 times 10 to the minus 7th molar, brackets mean concentration, right? Molar. So if we have an acidic solution, the first star, H plus concentration is larger than my OH minus concentration, but your Kw is still 1.0 times 10 to the minus 14th. If we have a solution that's overall basic, that means the concentration of OH minus must be greater than the concentration of H plus. But yet again, Kw, my dissociation constant for water, is still 1.0 times 10 to the minus 14th. So we can use that, okay? I put a box around it now because we can use it in calculations. Speak of the devil. Here's an example problem that's going to want us to do a calculation. So it says, in each of the following, calculate the hydrogen ion concentration, H plus, brackets, and the OH minus concentration. So that's OH minus in brackets, all right? So A says 1.0 times 10 to the minus 5 molar, OH minus. So they've given us the OH minus concentration. How are we going to find the H plus concentration? Well, Kw equals H plus times OH minus equals 1.0 times 10 to the minus 14, right? So H plus then is you got H plus times 1.0 times 10 to the minus 5th equals 1.0 times 10 to the minus 14. Finally, we clean it all up, and my H plus is equal to 1.0 times 10 to the minus 9th. There is a shortcut on how to do this, and I'm going to get to that in just a bit. Hold tight. You'll notice, look at the two boxes. The concentration of OH minus is greater than the concentration of H plus. So this solution is basic. All right, very similar one that I want to do is B. New page of notes at the top there, 10.0 molar H plus. They've given us the H plus concentration, therefore we have to find the other one, the OH minus concentration. Kw we know is 1.0 times 10 to the minus 14th, which is equal to the concentration of H plus times the concentration of OH minus. I've stuck in my H plus concentration, which is 10.0. Do some math. OH concentration, the OH minus concentration I should say, is 1.0 times 10 to the minus 15 molar. Remember, brackets are concentrations, the units are molar. Wow, the H plus concentration is way, way larger than the OH minus concentration. So whatever this solution is, it's very, very acidic. All right, so the last part of this video, video number 3 from section 14, acids and bases, is the pH scale. All right, first I'm going to introduce to you what the pH scale is, give you some sample pHs of some stuff that you've probably heard of, and then we'll start to do some problems where we calculate pH given the H plus concentration, or calculate H plus given the pH, etc. So the pH scale, first of all, pH is minus the log of H plus. It's also minus the log of H3O plus concentration, right? I keep forgetting to let you know that brackets are concentration. So this pH scale goes from 0 to 14. So 7 right in the middle, that's a neutral pH. Anywhere close to 7 we kind of assume is roughly neutral, but 7.00 is neutral. Acidic is less than 7, and a pH value between 7 and 14 would be considered basic. So down the list there, I've given you some pH values for some common household items. One that always strikes me strange is that milk is a little tiniest bit more acidic than water. That always was weird to me, that milk has a pH value of 6.80. But lemon juice you would expect to have a really low pH because it's very acidic, very tart, very sour. It's how acids taste. Don't taste acids in the lab, okay? Example, calculate the pH of the following solutions. A, 1.0 times 10 to the minus 3. B, 1.0 times 10 to the minus 5th. You notice how everything so far has been 1 times? Just take note of that. I'm going to tell you a shortcut here in just a second. All right, I'm given the H plus concentration. So pH is minus the log of H plus concentration. In other words, minus the log of 1.0 times 10 to the minus 3. If I put that in my calculator, I get a pH value of 3. So let's call it 3.00. It's always best to use 2 decimal places or the hundredths place for pH. It's just kind of how everyone does it. And there is a weird sig fig rule for taking the log of something. Just use 2 decimal places and you tend to stay out of trouble with that. B, 1.0 times 10 to the minus 5th molar H plus. pH minus the log of H plus minus the log of 1.0 times 10 to the minus 5th. So my pH is 5.00. Visually, you can probably tell if I just take the opposite of the exponent, I'm going to get the pH. And you're right. Here's the shortcut written out for you in your notes. Shortcut. Anytime you are asked to calculate the pH of a solution having a concentration of 1 times 10 to the something or other, like it could be 1 times or 1.0 times or 1.00 times, doesn't matter. If you have something with a concentration of 1 times 10 to the minus Z as in zebra, the pH is just Z as in zebra. For example, I'll do 3 examples here. 1 times 10 to the minus 9th molar H plus, the pH is 9.00. 1.0 times 10 to the minus 8th molar H plus, the pH is 8.00. Now, look at the 2.3. You can't take a shortcut here. 2.3 times 10 to the minus 7th molar H plus, there's no shortcut because the base number isn't a 1 or a 1.0 or a 1.00. You have to take the long route, which isn't all that long. You just do pH equals minus the log of that 2.3 times 10 to the minus 7th, okay? There is a similar log scale for pH, but using OH minus ion. Remember, OH minus kind of is your representative base concentration. So a similar log scale for POH. POH, well, first of all, pH was minus the log of H plus. So POH is minus the log of OH minus. Okay, very straightforward. pKw is equal to the pH plus the POH, which is equal to 14.00. So I put boxes around both of those because they're very useful. Very helpful if you commit those to memory because you use them a lot in acid-base calculations where you've asked to find pH, pOH, etc. Let's do an example problem. Calculate both the pH and pOH of a 2.6 times 10 to the minus 12 molar OH minus solution. You notice they gave me OH minus concentration. Because of that, let's work with the OH minus first. Let's find the pOH. So the pOH is minus the log of OH minus. The pOH is equal to minus the log then of 2.6 times 10 to the minus 12. If you do that in your calculator, you get a pOH of 11.58. All right, well, if I can remember that my pH plus my pOH must always equal 14.00, then I just have to subtract 11.58 from 14, and I get a pH of 2.42. Okay, pH of 2.42, that's acidic, right? So careful not to look at the pOH value, guys. Oh gosh, 11 something, really basic. No, that's the pOH. The pH has its own scale. pOH doesn't, right? The pH for that last guy was 2.42. That's acidic. Next example. The pH of blood, that was on our list earlier, is 7.41. Find the pOH, H plus, and OH minus. So basically find everything except for the pH which you're given. Well, if I remember that pH plus pOH equals 14.00, I can knock out the pOH calculation real quick, 6.59. All right, so that's done. Now, who do I want to find first? It's really up to me. Let's go ahead and find the H plus concentration first. So pH is equal to minus the log of H plus, but I'm trying to find that H plus. I don't want it tied up in a log. I'm trying to isolate my H plus. So minus P, if I go through this kind of rearrangement and stuff, I finally get it down to 10 to the minus pH equals 10 to the log of H plus. Then I have a little arrow there saying, oh, well, 10 to the log of H plus is just H plus. Well, what does that mean? Well, I'm going to put it right here in quotes. 10 to the log of something is just that something, right? If you've ever been in a math class, right, 10 to the log of something is just the something. So 10 to the minus pH equals my H plus concentration. I can't leave it as 10 to the minus 7.41. I have to do that on my calculator, and I get a concentration of H plus equal to 3.9 times 10 to the minus 8 molar. All right, so just punch that in the calculator and you get H plus concentration. Let's go back to my pOH and do the same route I just did with the pH to find my OH minus concentration. If you go pOH equals minus log of OH minus and then whittle it down, you finally come up with 10 to the minus pOH equals my OH minus concentration. Again, 10 to the log of OH is just OH. And that gives me a value of 2.6 times 10 to the minus 7th molar. All right, so this is every chemistry class I've ever taught or ever even sat in on or watched or helped someone with always has pH calculations like this, unless it's a very introductory chemistry course. So you want to know how to do these pH calculations, and these should be some very helpful examples. All right. Next video, we're going to talk about calculating the pH of strong acid solutions. We're also going to talk about calculating the pH of weak acid solutions. Turns out calculating the pH of weak acid solutions is a much more arduous task, and we have to reach into our section 13 stuff, the ice tables. Remember those? So stick around. Section 14 video number 4 is coming up next.